everyone, thank you so much for clicking onto the video. Today's learning objectives are to firstly be able to identify the amine and amide functional groups and molecules that are amino acids. We're then going to understand the reactions of primary aliphatic amines using butylamine as an example, with water to form an alkaline solution, acids to form salts, ethanol chloride, haloalkanes, and copper-2 ions to form complex ions. Now we're going to have a look at amines. So amines are another homologous series, and they have the general formula of R and then NH2. So R is an alkyl group, and then we have NH2. And they are thought to be derivatives of ammonia, just meaning that they've been made basically from ammonia. And what's different is that one of the hydrogens is replaced by an alkyl or an aryl, which is a benzene group. And we can get primary, secondary, and tertiary amines. So it's very similar to when we looked at primary, secondary, and tertiary alcohols. And to classify amines, we look at how many R groups are attached to the nitrogen. So what we have is first we have ammonia. So ammonia is NH3. So we have nitrogen with 3 hydrogens attached, and there's also 2 electrons, well, 1 lone pair of electrons on the nitrogen. And so this is ammonia. And then we have a primary amine. So that's where we have nitrogen and then 1 R group, and the other 2 are still hydrogens. And so this is a primary amine, and again we have the lone pair of electrons. And then we have the secondary. So this is where we have 2 R groups and a hydrogen. So this is a secondary amine. And then we have the tertiary amine, where we have 3 R groups attached to this nitrogen. And amines are very reactive compounds, and so they're really good intermediates in synthetic routes. And what that means is that they're very good at acting as the intermediate. So we form it in the middle of a reaction in order to form different functional groups that we want to get. And primary aliphatic amines can be prepared by the reaction of ammonia with haloalkanes and by the reduction of nitriles. And now remember that aliphatic means non-aromatic. So basically any molecules that don't have a benzene ring. So like all amines, so basically made of carbon and hydrogen in straight chains or branch chains or cyclic, just not aromatic. And aromatic amines, so ones which have the benzene group, can be prepared by the reduction of nitro compounds and are used in the manufacture of dyes. And now we're going to look at naming. So with primary amines, we use the suffix amine. So for example, we have CH3, NH2. So how we would name this is, because it's a primary amine, we have amine at the end. And then we have a look at what this group is. And this is a methyl. And so the name of this would be methylamine. So the amine takes priority, and the CH3 becomes a substituent group. And so similarly, we have ethylamine, which would have this formula. And we can also get one with a benzene. So we have benzene here, and if we have an NH2 attached here, this would be phenylamine, because again, the amine takes priority, and so it becomes the root of the name. With secondary and tertiary amines, we first name the longest carbon chain, and then place the name of the shorter alkyl or aryl group in front. And so, for example, we could have N that's attached to hydrogen, and then we have 2 methyl groups. So this would be called dimethylamine. Because the amine takes highest importance, and we have 2 of these methyl groups, and so that's why we use the prefix di. And then we could also get a nitrogen with a hydrogen and a methyl, and also an ethyl. And what we would do here is first we need the longest chain. So the longest chain would be this ethyl here because it's got 2 carbons. And so that's what goes with the amine, methyl ethyl amine. So this bit here is the longest chain we have. And so we treat this methyl as a substituent. Now we're going to look at amides. So amides are a homologous series with a general formula of CO and then a nitrogen. So we have a carbon with a double bond O, and this is normally bonded to a nitrogen. However, on this nitrogen, we can either have 2 R groups, or usually we have 2 H's if it's a primary amide, or we can have an R and a H, or 2 R groups. And so I'm just going to leave that as 2 bonds. And so this is what we normally use to identify an amide. And amides are the products of reactions of acyl chlorides with ammonia and amines. So these were the acylation reactions that we saw. And amide groups are common in nature. So for example, in proteins, the amine and carboxylic acid groups of amino acids are bonded together to form amide groups. Like amines, we have the existence of primary, secondary, and tertiary amides. And these depend on how many R groups we have on the nitrogen, again, like amines. So for example, for a primary amide, we could have propanamides. So we'd have 3 carbons in the longest chain, and then a double bond oxygen, and then we have nitrogen with 2 hydrogens. And this is propanamide. And then as an example of a secondary amide, we could have N-methyl ethanamides. And so this time we have, again, 3 carbons, but we have H3C, so CH3, a methyl group, and then this C double bond O, and then NH, but this time, instead of having another H group on the nitrogen, we have an R group, so we have a methyl. And so this is N-methyl ethanamide. And how we name this is that firstly we name the amide. So because we have 2 carbons here, it's an ethanamide because the prefix for 2 is eth. And then we have to use this N here to indicate that the substituent group that we're adding is on the N. So it's like when we have numbers, but this time we use an N to indicate that it's on the N. And this methyl is in the name because this is the group that we've added to the N. And then thirdly, for the tertiary amide, we could have N-dimethyl methanamide. So again, we have the 3 carbons, but this time we have H, C double bond O, N, and then this time we have 2 methyl groups on this N. So this is N, dimethyl methanamide. And this is our tertiary amide. So we can see that for the primary amide, we have an R group and then C double bond O, and then a nitrogen, and we have 2 hydrogens. And then for the secondary amide, we have an R group, C double bond O, a nitrogen, a hydrogen, and another R group. And then for the tertiary amide, we have an R group, a C double bond O, and then the nitrogen and 2 other R groups. And also for the tertiary amide, the reason we have to name it NN is because, like when we have numbers to label substituents, we have, even if it's on the same thing, we need to label it twice. So we have NN and then di because we have two of the methyl groups on this nitrogen. So we have dimethyl and then methanamide because we've only got one carbon now. So now we're going to talk about amino acids. 50 or more amino acids join together to form long-chain polymers called proteins, and these are vital for living organisms. They have two functional groups, and one is a carboxylic acid and the other is a primary amine. And there are 20 naturally occurring amino acids. They're described as either alpha amino acids or 2 amino acids, which means that the amine and carboxylic acid groups are attached to the same carbon. And all amino acids are optically active except for glycine. Now, the general formula of an amino acid is the amine group, and then we have a carbon, an R group, a hydrogen, and then we have the carboxylic acid. And R can be anything, it can vary. So, for example, R is equal to a hydrogen for glycine, or R is equal to a methyl group for alanine. So now we can see why glycine won't have optical isomers, because if we draw out the structure of glycine, H2N, and then carbon with two hydrogens, and a C double bond OOH. And so this carbon here, which is normally the chiral center, if we were looking at other amino acids, it's not a chiral center here because we have two hydrogens, so we have two of the same group on this carbon, and so we don't have four different substituents, and so we don't get optical isomerism. And so for an example of a 2 amino acid, we could have 2 amino ethanoic acids. So what that would look like would be if we had an amine and then a carbon, and then we had a hydrogen and another hydrogen, and then C double bond OOH. So that's how we can get ethanoic acid, because we've got two carbons, and amino because we've got the amine. And this is actually our glycine, but the systematic, the IUPAC name is 2 amino ethanoic acid. And so one thing you'll notice is that the carboxylic acid takes priority. So it becomes the root of the name. And also that means that the carbon which is attached to the double bond O and OH, this carbon is labeled number 1, and so this is 2. And so this is how we get 2 amino ethanoic acid. So we're treating this amine group here as the substituent. So now we're going to look at the reaction of primary aliphatic amines with water. So we've just learned that primary aliphatic amines can act as Bronsted-Lowry bases because we have that lone pair of electrons on the nitrogen available to form a dative covalent bond with a H+, and so accepting a proton. So when primary aliphatic amines react with water, they form an alkaline solution. So in this example, we're going to react water with, so butylamine has the formula CH3, CH2, CH2, and then NH2. So it has 4 carbons because that's why we have the prefix but. And so when we react this with water, what we get is the H+ of water being attracted to the lone pair of electrons on the nitrogen. And so we form CH3, CH2, 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 and then NH3, and then OH-, and this will be a positive ion. So what's happened is that water has acted as an acid, and this butylamine has acted as a base. It's accepted the proton. And so this is why we formed an alkaline solution because we have this OH minus here, which makes it alkaline. And it's also a solution because both of the products formed are charged. The next reaction we have to look at is the reaction with acids. So amines as bases react with acids to form ammonium salts in a neutralization reaction. And this is because the salt formed will be neutral. And the addition of sodium hydroxide to an ammonium salt will convert it back to the amine. The ionic salts formed in this reaction are soluble. So for example, phenylamine is not very soluble in water, but the ammonium salt, phenyl ammonium chloride, is soluble. And these ionic salts will be solid crystals if the water is evaporated because of the strong ionic interactions that take a lot of energy to break, and so they'll be solid. So the example we're going to look at is methylamine reacting with some hydrochloric acid. So we have methylamine, which is CH3 and then NH2. And then we're going to react this with hydrochloric acid. So what we get is CH3, NH3 plus, and Cl minus. And what we call this salt is methyl ammonium chloride. However, for acids which are diprotic, so they give off 2 H pluses for every acid, we could have, for example, again, this methylamine, but reacting with H2SO4 this time. What this means is that for every sulfuric acid we have to have 2 of these methylamines, because we can only provide 1 CH3 NH3 plus ion for every methylamine we have. And so what we form is CH3 NH3 plus, and we have 2 of these, and then we have the SO4 2 minus. And now the charges will balance out. So this is methyl ammonium sulfate. So now I'm going to talk about the reactions of primary amines with acyl chlorides. So we've actually already seen this reaction before when we looked at acylation. And this is where we introduce an acyl group into the primary amine. So again, the acyl group is this RC double bond O group. And the primary amine acts as a nucleophile. So it's got the lone pair of electrons on the nitrogen, which attack the acyl chloride. And what we form are secondary amides, or N-substituted amides. So the example we're going to look at is reacting methylamine with ethanoyl chloride. So what happens is that we have the ethanoyl chloride, which has the formula CH3, C double bond O, and then Cl. And when we react this with methylamine, which has the formula CH3, NH2, we can form N-methyl ethanamide. So we get CH3, C double bond O, and then we have NH, and then a methyl group. And we actually react this ethanoyl chloride with 2 of these methylamines. And so we also form this salt, CH3, NH3 plus, and Cl minus. And so the product is called N-methyl ethanamide. And that's because we have 2 carbons, so we use eth, and we use N because that's what indicates which substituent group is attached to. And then we have methyl because the substituent attached to the nitrogen is a methyl group. And this reaction can also be really helpful because we can produce paracetamol from this reaction. So how we produce paracetamol is we have an aromatic amine, which looks like this. So we have the benzene ring, and then we have an amine group and an OH group. And then we react this with ethanol chloride. And then we can form paracetamol. So we get the benzene ring, and then we have OH, and then we have and then C double bond O CH3. So this is our paracetamol. Now we're going to have a look at the reactions with haloalkanes. So when we react primary amines with haloalkanes, we can form secondary amines, and this is via a nucleophilic substitution reaction. And the primary amine acts as a nucleophile because of that lone pair of electrons on the nitrogen that it can donate to an electron deficient carbon to form a covalent bond. And the secondary amine formed can also then react with more halogenoalkane to form a tertiary amine, and then subsequently onto a quaternary ammonium salt. And this is because the secondary amine which is formed also has that lone pair of electrons on the nitrogen, and so can also act as a nucleophile. And that's the same with a tertiary amine as well. So the reaction we get is, for example, if we had ethylamine, so CH3, CH2, and then NH2, and we added this with some bromoethane, so CH3, CH2, Br, and this would form CH3, CH2, and then you'd have the nitrogen, and then 2 hydrogens, and then CH2, CH3. And we also form a salt. So we have CH3, CH2, and then we have NH3, and then Cl-. And in this reaction, we actually need 2 of these ethylamines. So the product we've formed is diethyl amine, because we have 2 of these ethyl groups attached to the nitrogen. And we started off with ethylamine, and bromoethane. Now we're going to talk about forming complex ions. So the lone pair of electrons on the nitrogen of these primary amines enable them to act as ligands and form dative covalent bonds with transition metal ions to form coloured complex ions. So as a reminder, ligands are species which have an electron lone pair available to donate to a transition metal ion to form these complex ions. And this is a similar ligand exchange reaction to the one where ammonia acts as a ligand. So if we've got a complex, a copper 2 complex, so CuH2O6, and we substitute 4 of these ethyl amines, what we get is that we can substitute 4 waters. So we have copper, and then CH3, CH2, NH2, and we have 4 of those, and then now we only have 2 waters left in the complex. And this still has a charge of +2, and now we have 4 waters which have been substituted out. So this is a ligand substitution. And so this is how we formed a complex ion. And this is actually not a straightforward reaction, but a reversible reaction. And what we're saying is that this is very similar to the ligand exchange reaction to the one where ammonia acts as a ligand. So if we've got the same ion, the CuH2O6, 2+, we've seen that if we add 4 ammonias to it, what we can form is the complex with 4 ammonias substituting the waters. So we have NH3, 4 and then 2 of these waters. And so the charge of this is still 2 plus because ammonia is also neutral. And again, we have 4 waters substituted out. And we know that this is the reaction where we start off with a blue solution due to the copper 2 plus ions, and then we end up with a deep blue solution.